We're going to look at worksheet number 4, question number 4, which is one of those two-dimensional conservation of momentum problems with a funny angle involved. We've done the two-dimensional conservation of momentum problems with right angles, and they're relatively straightforward. They're really just the same thing as we have spent a fair bit of time on, PI is equal to PF, except you got to do the PI equals PF twice, right? But no real crazy, difficult additions to it, except it's more work. These ones do have a little bit more difficult of an addition to it, albeit a grade 10 math trigonometrical, is that a word? Trigonometric addition to it, but still an addition that makes it a little bit different. Let's draw a picture of this. Whenever we see a two-dimensional problem, we should draw a picture. And a two-dimensional problem exists whenever we see north and west in the same problem, or a funny angle, like 30 degrees south of west. We always need to break it up into X and Y, and we always need to draw a diagram here. This is what we call a situational diagram. It's not a vector diagram. There's no real firm rules on how you draw this, whatever makes the most sense to you. The vector diagram has to be drawn a certain way. The situational diagram should be drawn the way that makes sense to you. Okay, this is the way that I'm going to draw it. This 400 kilogram bomb is sitting there at rest on a table. It explodes into 3 pieces. One goes east at 150 meters per second. I'm going to call that piece 1. I'm going to label it as 150 kilograms and 150 meters per second. Now we have another one going south of west. I'm going to call that piece number 2. And I'm going to label this as 30 degrees south of west. I'm going to label this velocity as 200 meters per second and the mass as 100 kilograms. Now, some people get mixed up a little bit as to the south of west, west of south thing. Okay, draw it out the way you think it should be drawn, and then just check your drawing. Okay, is that south of west or is that west of south? Well, I measured this angle from which axis? There's a west axis here and there's a south axis here. Did I measure the 30 degrees from the west or from the south? From the west. And then from the west, I went south. South from west, right? South from west, or south of west. So that's correct. The way that I drew that is correct. Now my third vector, I don't know where that goes. I don't know where exactly it goes, but I do know the vicinity of it is going to be up here somewhere. It's going to go up and probably to the left. Its mass is 150 kilograms, and we know that because 400 minus 150 minus 200, minus 100 gives me 150. That's its mass. We just need to find its velocity now. Okay, that's what we're looking for. Okay, so what's the first step here? Well, that's the first step. What's the next step? I don't like funny angles. We have one funny angle to deal with here. It's 30 degrees. So we take it off to the side. Doesn't matter whether it's down here or over here, whatever. Okay, somewhere off to the side and redraw it. There's my 30-degree angle. There's my x component. There's my y component. And it's a 200 meters per second vector here. All right. So this is our grade 10 math part here, right? That I'm not trying to insult you if you're having trouble remembering this. I forget math stuff that I learned years ago, right? We forget stuff. But my point is not that you necessarily remember it. My point is that you've learned it and you can do it. If you forget it, you just need to have it come back to you, right? You can do it. You just might not remember it, but you're capable of doing it. Which side of the triangle is that x? Which side of the triangle, Cameron, is the x? Is it opposite, adjacent, or hypotenuse? It's adjacent, good. So adjacent, 200 is the hypotenuse, right? Adjacent and hypotenuse goes with which trig function? Adjacent hypotenuse. Cosine, yeah. So we're going to say cosine 30 degrees is equal to adjacent, the x over the hypotenuse 200. X is going to end up being there 173.205 meters per second. And for the y component, it's got to be the other one, right? Sine 30 degrees is equal to opposite over hypotenuse. Y ends up being equal to 100 meters per second. Now, I always box that off. There's no real good reason why I have to box that off, but I do just to kind of set it aside because that's the way I think of this step as oh, this is a step that I kind of have to do, but it's not part of the main question. Okay, the main question is our PI is equal to PF. So let's put it off to the side here just to kind of keep it separate from the main part of the question. Okay, X and Y. For the X component, we know if you finished your lab that's due today at 3:30, then you would know that the X component of momentum should be conserved. So we'll say for X, PI is equal to PF. By the way, the Y component should be as well. PI is equal to PF. What's the initial momentum? I'll tell you, what's the initial momentum of this bomb before it explodes? It's 0 because it is, yeah, it's stationary, it's at rest. So we could put a term in there, m total times VI, but if we did that, VI would be 0 and the term would become 0. If you recognize that right away, just put a 0 in there. Sometimes you don't. Like sometimes you just kind of get in this groove of writing letters and numbers in there. That's fine. Okay, it becomes 0 later on. It doesn't really matter. I caught it now, so I'm going to write it down now. 0 is equal to, how many objects do we have, Nick, after the explosion takes place here? 3. So I'm going to write in M1 V1F plus M2 V2F plus M3 V3F. And I always wish for, in a question like this, the masses to be the same. They're not here. But why do I wish for the masses to be the same? Yeah, if it appears in every term, you can cancel it out. That doesn't happen here.
I thought you said and.
No, yeah, that's what I said, yeah. Okay, so M1 is 150 kilograms. V1F, what's V1F? What is V1F? Parker, what's V1F? This is X component. V1, object number 1, final. And yeah, it's 150. Mass is 150, so is the velocity. Okay, mass 2 is 100 kilograms. What's V2F? Nicole, what's V2F? No, the 200. We never want to see that again. Okay, we never want to see that again, right? That's the reason we took that over to the side, right, is to get rid of that 200. So what is it? 173. Do you see why it's 173? Yeah. Okay. We're actually going to make it negative, though, because it's left, because it's west. Let's highlight that. So you can see where that comes from, right? Negative 173 because it's to the left. Plus M3, which is 150 times V3F. And we solve for that. V3F it works out to be negative 34.53. Guys, you got to make sure that you can get that. I just heard somebody say, I did not get that. Okay, that's fine. That's okay. No, that's okay. But no, that's okay because we make mistakes with that, right? So you're going to ask me right now, how do I get that? And I'm going to help you. How do I get that, right? Okay, this is the key. This is the key to really doing well here. Okay, is obviously paying attention, which for the most part, you guys do a really good job at that. Now, the key beyond that is like internalize what's happening here. Like it's one thing to watch me doing that and say, okay, that makes sense. Yeah, that makes sense. Just like if Mr. Aiello in phys ed class teaches you to throw a free throw in basketball, you can look at him, he does it 100 times, demonstrates it for you, and you say, okay, that makes sense. I can do that. Well, then go try it. When you go try it, it seems harder than it does when you're watching sometimes, right? Like the key is like to really learn it, you got to do it. You can watch me do this and say, oh, this makes sense. But if you don't do it, if you don't punch the numbers into your calculator yourself, if you're not physically doing it as I do it, then it's not going to make as much sense to you as if you do it. All right? Yep, Jacob. How to get a negative? Okay, let's calculate that. Okay, on our calculator. We're going to say 150 times 150. That gives me 22,500. So that first term, 22,500, and then the next term is 100 times 173. Yeah, so I'm going to make that subtract 173,205. Does that make sense? I could add a negative, and that's fine, or I could just make it subtract now. Plus 150 V3F. So now what I'm going to do is combine these simply by adding or subtracting, I guess. 22,500 subtract 173. Okay, so that's 5179.5. And then what am I going to do, Jacob, now? Yeah. So it becomes negative 5179 divided by 150. And I sure hope I get 34. I do. Negative 34.53. Does that make sense? Okay. But again, guys, if you're watching me doing it is one thing, doing it is another thing altogether, right? That's what really sets you apart if you're doing it yourself. Okay, I'm going to erase this. And now I'm going to go to the y component. And now I'm going to go to the y component here. Once again, pi is equal to pf. 0 initial y, just like there was for x. Oh, almost missed this. Almost missed this. What is m1 v1f equal to for the y component? 0. Good. Because it's only on the x-axis here, right? The y-axis is what we're looking at. That's going to be 0. M2 is 100 kilograms. What's V2F for the y component, Tim? Yeah, we're going to make it negative because it's downward. So that's where that comes from. Again, that whole 200 meters per second, that's gone now, right? That's completely gone forever. Add that to 150 times V3F. This one's, Jacob, I think you agree that this one's easier to solve for. Multiply these two together, take it to the other side by adding, because it's a negative number, and then divide by 150. And for that one, we're going to get 66.667. And it does work out to be positive. So there's my x, there's my y. Now I'm just going to combine them, right? 34.53 to the left, 66 up. This is going to be V, and this is going to be theta. Always draw that angle at the start of your diagram. If I'm giving you directions somewhere, or if you look on Google Maps for directions somewhere, it doesn't give you directions from the end. It gives you directions from the beginning. So if I'm expressing a theta here, an angle, I want to express it from the beginning of my vector diagram, not the end of it. Okay, I don't want to find this angle. I want to find this one. Okay, how do you find V? I won't do the work here, but how do you find it? Pythagorean theorem, a squared plus b squared, yeah, equals c squared. V works out to be 75.1 meters per second here. Theta, a little bit harder, the inverse tan of opposite over adjacent. What's opposite? 34 is 66. 66 over adjacent. That's going to work out to be 62.6 degrees. Is that, we were going north and we're going west here. Is this west of north or north of west? Yeah, we're going like, we're not measuring the angle from the north. We're measuring it from the west, right? This is west, measuring it from the west, but yet we're going north from the west. So we're going to say that this is 62.6 north of west at a speed of 75.1 meters per second. Okay. I'm going to have you guys work on question number 5 here at your desks. I will give you a word of caution for question number 5, a couple words of caution. Firstly, question number 5 has 4 objects afterwards as opposed to 3. That doesn't make things harder. It just makes things longer. Yeah, a little longer, that's all, right? Secondly, watch this angle. Okay, watch this angle right here. 30 degrees west of north. Means we're measuring it from the north and we're going west from the north. Okay? The temptation there is to label it like this. Okay? This would be wrong because this is labeling it from the west. This one is labeling it from the north. Got it? Okay. Give it a try. Give number 5 a try, and then we'll take a look at that one in a little bit once you've had a chance to work on it. So look at number 5 now. It says a bomb sitting at rest on the table explodes into 4 pieces of equal mass. There's good news and there's bad news with that sentence. The bad news is there's 4 pieces. So it's a little bit more to deal with, right, than the other questions we've dealt with. What's the good news in that first sentence? What is it? Yeah, the masses are equal, which means what's going to happen? They're going to cancel each other out, right? Now remember that you can't just automatically cancel masses in most things that we do just because they're equal. Conservation of momentum, you can because of the nature of the terms, right? If they're equal masses, then it'll be the same mass in every term. That doesn't happen with impulse. It doesn't happen with most of the things that we do, but it does here. So it is good news that we can cancel out those masses. We got one piece going one way, another piece, third piece, and then finally we want to find the velocity of the 4th piece. Let's draw a picture, our situational diagram here, and we can draw it whatever way makes us comfortable with this. Okay, it's our vector diagram that has to be drawn a certain way. This is where my explosion point is. I get a first piece going south. I'm going to label that piece number 1, and I'm going to make that 55 meters per second. We have piece number 2 going to the west. Okay, I'm going to make that 80 meters per second. And I got piece number 3 going at west of north. Okay, this is piece number 3, 30 degrees west of north. Okay, we're saying that we're measuring from the north, from the north, but yet we're going west from the north, or west of north. Okay, the value of that is 40 meters. 40 meters per second. And then the third piece, I don't know exactly where it's going to go. I do know that it's going to go to the east, but is it going to be north and east or south and east? I'm not really sure at this point, but I'm going to guess it's up here. But in the end, if I'm wrong, it's not the end of the world. That final vector that you're trying to find, it doesn't have to be drawn perfectly. That's more to help us visualize what's going on. If we do draw it well, it helps us to see it a little bit better. But if we don't, then it's not the end of the world. Okay, next, Parker. We got a funny angle here, right? Take it off to the side, redraw it up here. 30 degrees. Let's make this Y. Let's make this X at 40 meters per second. We don't want that 40 meters per second, right? That's why we take it off to the side, to get rid of it. Which side of the triangle, Parker, is the X side? Is it opposite, adjacent, or hypotenuse? It's opposite. Good. So that's going to be which trig function? Opposite sine, right? Opposite and hypotenuse is sine. Sine 30 degrees is X over 40. And that works out to be 20. That means that the Y component must be, Nick? Yeah, and therefore it's cosine, right? Cosine 30 degrees is equal to Y over 40. 40 cosine 30 is 34.641. And I always box that off just to remind me that it's kind of off to the side and doesn't form part of the main question. And now it's this. Like you cannot just say PI equals PF. You can't do that because momentum is a vector, direction matters. There is an X and a Y direction. You have to account for that. So we're going to break it into X and Y. PI is equal to PF. Can you tell me what PI is for both X and Y? Yeah? Now, unfortunately, we have 4 terms here. M1V1F plus M2V2F plus M3V3F plus M4V4F. But the good news is, we touched on this earlier, the good news is, somebody? Masses are the same, so they end up canceling. V1, oh, I missed this. Even better news, even more good news. What did I just notice that I didn't notice before? V1F is 0 as well. How come? It says it's 55 there. Yeah, that's the y-axis, and I'm dealing with the x-axis right now, right? So we're going to say 0 is equal to 0 plus V2F is 80? Negative 80, good, Ben. Plus V3F, which is not this 40, right? That's gone. Not this 40. What's V3F? X component. No, not 30. Yeah, it's 20, but it's also left, also less, so we're going to make it negative 20. Let's highlight that to remind us of where that came from. Plus V4F. So negative 100, take that over by adding, it's positive 100. So V4F equals 100. There's my X component. Okay, Y component. I'm going to do the Y component down here. Remember, this goes with question number 5, though. Just to make some space here. PI equals PF. 0 initial momentum equals M1V1F plus M2V2F plus M3V3F. You can cancel out the masses here as well. Because they're the same in every term. V1F. V1F. Cameron, what's V1F there for the Y component? How fast is object number 1 moving Y-axis after the explosion? 55. We're going to make a negative because it's downwards, though. V2F. Taylor, what's V2F? 0, good. I could have just wrote the term 0 in there above if I had caught that. I just didn't. V3F. V3F. Benton, what's V3F here? Good, and it's positive because it's upwards. I'll highlight that to remind us where it came from as well. 34.64. Remember, it came from that 40 meters per second, but we don't ever want to use that again, right? We changed the 40 into a 20 and a 34. V4F works out to be 20.359. There's the Y component. And now it's the easy part, I think. At least for me, it's the easy part. Okay, maybe the other one was the easy part for you. 100 to the right, 20.359. Solve for V, solve for theta. This is what we could theoretically send down to Math 10-1, and they would tell us that I would solve for V using the Pythagorean theorem, get a value of 102. and it would solve for theta using the tan function, and we get 11.5 degrees. What would that be? 11.5 what of what? Yeah, we're measuring it from the east, not from the north. I'm measuring it from the east, but we're going north from the east. So it would be 11.5 degrees north of east. All right? Does it feel okay? Okay. Let's do another one. Or you will do another one, not me, because I've already done it. But now I get to take a look at number 6. I'll erase this in a minute, but just let me point out something in number 6 that maybe you need drawn to your attention. Number 6, we're back to having 3 objects instead of 4. That's good news. The masses are not the same, which means we can't cancel them. And finally, this bomb is moving before this explosion takes place. What wrench does that throw into it? It's not a serious one. Instead of the initial momentum being 0, the initial momentum will be m total times vi, right? Just mv, just an extra term in there. But we have one less term on the right side, so it's not really that much more. Okay, let's get at number 6 here now, please. Let's have a look at number 6 now, everyone. It says a 200-kilogram bomb moving west at 10 meters per second explodes into 3 pieces, and then the 3 pieces go off here. Now, I've told you a few times now that the situational diagram is drawn the way that makes sense for you. Right? There's no rules on how you draw that diagram. This one's a little tricky to draw, I think, because we have that initial velocity and then this explosion. This is the way I'm going to draw it. Initially, I'm going to draw it as if the object is at rest. Okay, there's my explosion point. I've got one piece going off this way. Piece number 1, it's 100 kilograms. It's got a velocity of 90 meters per second. I've got piece number 2 going at 30 degrees north of east. That's going to be up here. Okay, this is 30 degrees, and this is measured from the east, but north from the east. The mass of this one is 55 kilograms, and its speed is 55 meters per second. The third piece, we don't know exactly where the third piece goes, but we're going to guess down here somewhere. Okay, its mass here is what? 200 minus 100 minus 55. Going to be 45 kilograms. Is that right? That's what we're trying to find. The velocity here. Now, I'm going to just draw a little vector over here saying VI is 10 meters per second this way. Again, there's no rule on how you include that in your diagram. This is a situational diagram that describes the situation to you, the person who's solving this question. So draw it the way that it makes sense, but include everything so that you don't miss something when you're doing the math here. Okay, now at this point, my solution should look exactly the same as your solution. We take off the 55 meters per second off to the side here. 55 degrees, this is x, this is y, and this is our 55 meters per second. X is going to be found by which trig function? Sine or cos? Cosine, because it's the adjacent side with the hypotenuse. X works out to be 47.6314. Make sure you can get that. If you can't, let me know and I'll help you out with it. The y component is using the sine function, its opposite side. It works out to be 27.5 meters per second. Box that off. Yeah, go ahead. Did I make a mistake there?
Isn't it 30 degrees?
It is 30 degrees. Yes, yeah. You're right. And when I did my answer, of course, I was just looking at my answer sheet. So the answers are correct there. But you're right, it is 30 degrees, yeah. Okay, so now we go, all of us, we'll do the same thing. We go to the x and y components. We say pi is equal to pf. Usually in these explosions, at this point, we say the initial momentum is 0. But it isn't here, right? Nicole, what is it here? Yeah, we're going to say m total times the initial, right? Which is, you're right, negative 2,000 when we do the math there. Equals m1 v1f plus m2 v2f plus M3V3F. We cannot cancel the masses out here, unfortunately. Total mass is 200 times, Nicole said, negative 10. Yeah, that comes from there, right? The initial velocity. M1 is 100 times negative 90, right? Because it's to the left. M2 is 55 kilograms times, what's our velocity here? Not 55, right? That's gone forever. What's our velocity? Yeah, 47, and it's positive, right, Parker, because it's to the right. 47.6314. Good. Okay, let's highlight that so we remember where it comes from. Okay, the x component there. Plus M3, which is 45 times V3F. So let's get this number. Let's combine these numbers, and then let's take this number over. Don't divide by that. Don't combine that with a 45 over here. Like, combine these, and then take it over to the other side by adding or subtracting as necessary. And then take this over, after you're done all that, by dividing. When we do that, we end up getting V3F of 97.3394 meters per second. That's the x component. If you have trouble with the math there, with the algebra, let me know, because I want to help you with it. I just don't want to spend 10 minutes going over it in class if we're good with it, that's all. Y component. Get a bit of a break here. Somebody said, Cameron, I think it was, said what the initial momentum is for the y component is what? Right, because it's, although it's moving on the x-axis. So we've got to include that, or we don't have to include it here. We did for the x. And now 7 numbers here. M1. Oh, wait. Oh, get another break here. What's M1 V1F equal to? 90 meters per second here, but it's all on the x-axis, so 0, right? We could have just subbed in a value of 0 for that. I didn't catch that at the time. That's okay. I caught it now. So it's 0 plus M2, 55, times V2F. We don't want that 55 speed. Rather, we want V2F. Austin, what's V2F? Good, 27.5. Positive or negative? Yeah, because it's to the right. Or sorry, because it's up, right? Not because it's to the right, because it's up. We'll highlight that one. Make sure where it's coming from. Plus M3 is 45 times V3F. This one's easier to solve for. You're going to combine these two terms. Take it to the other side by subtracting, then divide by 45. V3F works out to be negative 33.611 meters per second. Now we combine them. 97, 33, V gets found by, Taylor V gets found by what? Yep, and it works out to be 103. The Pythagorean theorem gives me 103, and theta is found by the, which trig function do I use there, Janae? Tan opposite 33 over 97, opposite over Jason, gives me 19.0 degrees. 19.0 degrees what of what? Where am I measuring it from? Am I measuring it from, we're going south and east, right? Am I measuring it from the south? Am I measuring from the east? From the east, so it's going to be south from east or south of east. Good? How many people got that one? Or were well on their way, maybe didn't have quite a chance to finish it off, but were going to get it if they had time. Good? All right. Number 7. Have a look at number 7, please. That's going to be the last one that I'm going to ask you to do today.